When I think of torque, I like to think of a seesaw. And so let's say you're standing on this side of the seesaw. Obviously, the seesaw would rotate this way. And so we'd say that you're exerting a negative torque on the seesaw because you're making the seesaw rotate clockwise. And so clockwise is negative generally. That's basically just the convention for torque. And if you were standing on this side of the seesaw, then obviously it would rotate the other way. And so the torque you'd be exerting is positive, since positive is counterclockwise. But what if you got your little sister to go on the seesaw instead? Well, since she doesn't weigh as much, then obviously the seesaw would still rotate in the same direction, but just not with the same amount of speed. And so we've found one variable that affects torque: force. So you'd be exerting a greater amount of force on the seesaw because you weigh heavier than your little sister. And so the seesaw would rotate more or faster, and your little sister doesn't weigh as much as you, and so the seesaw would rotate slower or not as much. Well, what if your little sister stood over here instead? And so now that she's closer to the middle of the seesaw, then the seesaw really wouldn't rotate that much, because since she's so close to the axis of rotation, her exerting a force on the seesaw is barely going to do anything. So now we've found another variable that influences the torque, and that's going to be the distance that the force is being exerted at. Let's look at another example. So let's say this is a door, and here's the doorknob, and you exert a force over here, which is all the way to the left of the doorknob. Even if you exert a really huge force over here, the door might just rotate a little bit. If you put your hand on the doorknob and exert a force here of the same magnitude, then the door would easily swing open. So that verifies our idea about the distance affecting the torque. Well, let's say that you put your hand on the doorknob again, and you just give it a slight push. Again, the door would only swing open a little bit. But if you put your hand on the doorknob and shove it with all your might, then the door might violently swing open. And so that also verifies our idea about force having an impact on torque, because the larger the force you exert, the greater your torque. But what if you started pushing the door on the side over here? Well, from a bird's eye view, it would look like this. So this is the top of the door, and the doorknob is somewhere on this face of the door. So initially we said that we're exerting a force on the doorknob, and that worked out perfectly. The door swung open. But if you exert a force on the side of the door, then clearly nothing would happen since there's a wall over here that's stopping it from moving. And it wouldn't rotate because the force that you're exerting is parallel to the door. In other words, you need a perpendicular force being exerted on the door in order to make it rotate. So it would work if you pushed over here or on this side. So what can we do to this expression to fix it so that we make sure that it's accounting for whether the force is perpendicular or parallel? Well, let's try to visualize this another way. So we have the door here again and the doorknob. And let's say the force we exert is on an angle, and this is the angle here, theta. So this force, we'll just label it F, has both x and y components. And the x component would be considered parallel to the door, because it's going this way. And so remember, if we push it this way, then nothing will happen. It will not rotate or anything. What we need is the perpendicular aspect of the force, which is going to be in the y direction. And so if we want to get this, then we'll have to use sine theta, which is opposite. So this is the opposite side. Let's just label it y because it's the y component of the force, over hypotenuse. So that would be the magnitude of the force vector. And so to solve for y, all we need to do is multiply both sides by f, and these two cancel out, so f sine theta is equal to y, or the perpendicular aspect of the force vector. And so instead of simply just force times distance, we can use f sine theta times distance. And now our new expression for torque would be f sine theta times d.